Hey, this is Tony from Adafruit, and in this video I wanted to take a quick diversion from some projects I'm working on and look at how to compile and use MicroPython on the Feather nRF52. So this uses the Nordic nRF52 processor or module, which is a really neat little module. It's the next revision of the nRF51, which we've had in the Bluefruit LE friend module. The microbit uses the nRF51. Really nice little processing module that has a nice little ARM Cortex processor and a full Bluetooth low energy wireless stack so that you can communicate with devices like talk to a smartphone or a tablet using Bluetooth low energy. So the nRF51 was pretty nice, but it was a little bit low on memory. If I remember correctly, it only has like 16 kilobytes of memory. And then once you get MicroPython running on top of that, you lose a lot of that memory to MicroPython's uses. So you don't have a ton of capabilities. But the nRF52 is really nice because it has a lot more memory and a lot more capabilities. So it should hopefully be a better platform for using something like MicroPython. And I noticed there's an early port of MicroPython to the nRF52 that supports the Feather nRF52 and lots of other nRF52 dev boards. So I thought, let's take a quick look at that port. We'll see how to compile the firmware for it and how to install the firmware in this video. And like I said, it's kind of early days. It's not an official part of MicroPython yet. It's a fork that someone made, Daniel Trolazzo. We'll see his name on the GitHub repository. So it's not maybe as stable as upstream MicroPython yet, but who knows? In the future, hopefully it might get pushed upstream and we'll have a nice port of MicroPython to the nRF52. So let's just kind of dive in. We'll go through kind of the process of how to compile this firmware, because like I said, it's not an official port yet, so there's no pre-built firmware that you can download. And because it's so new and changing and maybe still a little buggy, you're going to want to compile this and kind of stay up to date with it. So a little more advanced than just loading MicroPython onto an officially supported board. But you'll see it shouldn't be too bad. We'll use a little Vagrant-based virtual machine to compile the firmware and to also flash it onto the Feather nRF52 using this process called the Dfu. I believe it's like the device firmware update they call it. So you can update the firmware over the little USB port on the Feather board for this, which is kind of nice using that Dfu technology. But you'll see there are a few little tricky things to get this to work. There's maybe some stuff, there's a little bit of documentation on it, but I'll kind of walk you through and show you some gotchas and some caveats to get the firmware built and how to load it onto your board. So let's just kind of dive in here and we'll get started. Let's see, we'll go to the main view real fast. Let's go here. Cool, and let's see. So in the upper left here, this is the nRF52 Feather, like I mentioned, and I'll put it right here. And I'll put a link to the Feather board in the shop. So it's this board right here. And let me just put this onto this breadboard real fast. Like I said, it's a nRF52 based development board in the Feather form factor, so it's nice. You can snap on all the different Feather wings and things, put like an OLED display on top of this board. It's supported in Arduino, so we have an Arduino package that you can install and you can compile and write code that runs directly on this little nRF52's processor, and it's pretty nice. So this mentions the capabilities. With the nRF52, it's an ARM Cortex M4F, which just means it's a fancy, fast, one of the fastest ARM Cortex-M processors you can get right now. So 64 megahertz speed. The F means it has hardware floating point, which is really nice. So if you're doing math operations, they'll be a little faster and more accelerated using this board. But the thing I think is really nice, it has 512 kilobytes of flash memory. So that's where like you can store your Python code and things like that. And 64 kilobytes of RAM. So that's double the RAM on like the SAMD21 board that's really popular and used a lot right now. So you have a lot more RAM for your programs and things in MicroPython. And so this Feather form factor makes it nice in that you've got a little LiPo charger built into it. All of the pins and things are easy to get to with it. And there's a USB to serial chip on it already. Because kind of like the ESP8266, you need to add that USB to serial chip to make this work. And this is a Scilabs chip, just like we use on the ESP8266 Feather Huzzah. So just a note, on OS X and on Windows, you'll need to install a driver in order to access this chip. So before you get started, check out the product page, and there's a link to the tutorial and the guide on this chip. And so definitely follow the tutorial. You'll have to solder the headers onto the board, but this mentions how to get the driver installed that you're going to need, and if you want to set it up with the Arduino processing or Arduino system to program it. Not a bad idea to use Arduino. Just make sure you can load a basic test sketch on the board before you get too deep into this. Like I mentioned, this is a fork of MicroPython that this Daniel Tralamazza, I believe that's how you pronounce the name, made. And so he just forked MicroPython and added support for the nRF52 and a few different nRF52 variants, or at least dev boards. So the Feather nRF52 is supported, and then I think some of the development boards are also supported that you can buy here. And like I said, it's a fork of MicroPython, so it's not in the main MicroPython branch yet. I believe it's based on probably the 1.9 release of MicroPython, but it might be earlier than that. So just, be careful. For example, the libraries changed in MicroPython 1.9. So if you've compiled a library with MPY cross for the 1.9 version of MicroPython, you can't use it on older versions like this. So, just be careful. You might need to dig in and figure out which version this works against, or just recompile your code with MPY cross using this repository's version potentially if you run into issues. Now, all of the nRF52 specific stuff is in this nrf directory here, and this gives you some basic kind of guidelines on what you need to do to compile this. So it mentions you basically need to clone this repository. You need to initialize the submodules in the Git repository. This is standard for a MicroPython repository install. You need to tell Git basically that you've cloned the repository and to clone all these sub-repositories that it has. So that's this magic line right here. Then you make the MPY cross tool, and then you go into the nRF52 folder, like I mentioned, and then you can use the make command to build the code inside of there. Now, all of this assumes that you have a POSIX or a Unix-based build environment set up, like something that has the make tool, something that has the GCC ARM cross compiler installed and in your path, for example. So that's, if you're on Mac OS X or Linux, then you're pretty much good to go, although you're going to need to make sure you have that ARM cross compiler installed. If you're on Windows, it gets a little trickier. With Windows 10, you might be able to use the Linux subsystem in the Creators Update. Or what I would recommend, regardless of if you're on OS X, Linux, or Windows, check out using a Vagrant-based virtual machine. So we'll make a little virtual machine on your computer that runs Linux. We'll just run a version of Ubuntu or Debian Linux. And then we'll install all of these tools into that virtual machine. So the cross compiler, it's got the POSIX build environments, it has the make command, everything you need for that to compile MicroPython is going to be installed in there. And so that's kind of nice, and then it puts all those tools into a little virtual machine. You can connect to that virtual machine, compile the firmware, and then we'll see, we can even flash the firmware from that virtual machine. So to do that, you'll actually want to check out this old MicroPython for SAMD21 guide, where I mentioned how to use a virtual machine to build, at the time, what was our MicroPython SAMD21 firmware. And this little Vagrant box is actually pretty handy because it installs the GCC ARM cross compiler into the Vagrant virtual machine. It also installs the CircuitPython source code, but you don't have to use that. This VM is useful just with that cross compiler set up and installed already. So we'll do that. Let's use this Vagrant virtual machine. We'll use it as the base for our nRF52 firmware compiling, and then we'll go from there and use this tool. So what you'll want to do is you'll want to check out this page, and I'll put links to all of these guides in the description below. So when this is up on YouTube, just check out the description below and you'll see a link to this guide. And you can see all the details on everything that I link to and mention. But anyways, read this page. This explains the basics of Vagrant usage. So you'll need to install a couple tools here. They're all open source and free tools, which is really nice. So you'll need the Vagrant tool. That's basically the tool that manages this virtual machine. It gives you a command line interface to create the virtual machine. Then you'll also need the virtual machine itself, and so we'll use VirtualBox, which is a free and open source virtual machine tool. It's cross-platform, works on Linux, Windows, and Mac. So install both those tools, and this guide mentions where to get those tools. And then you'll need also Git installed because you need to clone this Git repository. But once you do that, and this is the Git repository right here that has this little Vagrant virtual machine. Once you do that, so I've cloned that repository already, and then you'll go into the directory where you've cloned that repository, and you'll run this command. So you'll run Vagrant Up. And what this is going to do is it's going to actually create this virtual machine. So it's going to spin up the virtual machine. The first time you run this, it's going to take a little while. It might take like 30 minutes, maybe an hour sometimes, because it's actually going to download an entire Linux operating system. It's not going to get like a whole graphical user interface. It's just going to get a real minimal system that can really only run command line tools. But it's going to give us enough to compile the MicroPython firmware. Now the nice thing is it only does this once. The very first time you run that Vagrant Up command, will it do what's called this provisioning process, where it downloads the whole operating system. The next time you run it, it's going to be fast like this. It's just going to take a minute or two for it to start the virtual machine back up. But okay, so now my machine has been run, and I provisioned this ahead of time because you probably don't want to watch 20 minutes of this thing downloading things while I run this stream. And anyways, if it's downloading things, it's going to ruin my upload bandwidth anyways. So my machine is provisioned, but I haven't done anything else. I've just run that Vagrant Up once, and then you want to run Vagrant SSH. And this is going to connect to your virtual machine. So it's going to actually connect to the Linux terminal inside your virtual machine. So even if you're running Windows or Mac or whatever, after you run that Vagrant SSH command, you're inside of a little Linux machine that's running on your main computer here, which is always kind of a fun thing. I always enjoy using virtual machines. Okay, so once this is set up, it kind of drops you into this folder where you have the BOSSA tool, and then there's also a source directory. These are specific to CircuitPython. This is where you can get the CircuitPython code, you can compile the firmware. Like I said, this virtual machine was originally for building CircuitPython stuff, but it has the GCC ARM cross compiler installed, so it's useful for compiling other stuff that uses the ARM code. So at this point now, we're ready to grab the fork of MicroPython that supports the nRF52. So what we'll want to do is grab this GitHub repository here, and we want to grab the link that they have here to clone this repository. So I'll copy that. And then in my Vagrant VM, just from the root, I'm just going to clone the repository into there. So we'll say git clone, and we'll paste in that address. And so that's going to copy the source code for the repository down. And like I mentioned, the way MicroPython is structured right now, pretty much at a high level, each of the subdirectories in the MicroPython repository are specific ports of it. So there's like, the TI CC 3100 and 3200 port. There's the STM HAL, that's for the Pi board, for example. So in this case, they've added an NRF folder, which has the nRF52, and I believe it also supports the nRF51. But like I said, the 51, there are multiple MicroPython ports to that one. There's one for the microbit. There's this one that probably supports it. Who knows? There could be other ones for this. Eventually, I think, hopefully, all of this stuff will be pushed upstream into the upstream MicroPython. Maybe this time next year, there'll be like the one NRF folder that's the official one. But for now, we can use this one. Anyways, it's really everything in this NRF folder that we care about. And so that's, again, where there are some of these basic compilation instructions in here. So this mentions, okay, so we've done this first command. We've cloned the repository. And then we need to go into that repository and run this submodule initialization command. So I'm going to copy that. And as you can see here, this created this MicroPython folder. So I'm going to go inside of there and then run that submodule init command. And so this is just downloading some Git repositories that are inside of this Git repository. It's just Git repositories all the way down. So this is going to pull in all of their code. From what they include, it's stuff like TCP/IP libraries that like the ESP8266 uses, SSL, TLS implementations, stuff that MicroPython doesn't want to re-implement. So it makes sense. Let's pull in some other open source packages and use those. Okay, so Git just did its magic, and you just have to do this once. This is just some initial setup for this repository. Okay, and then at this point, you want to make the MPY cross tool. And so that's what this command will do. This is going to go into the MPY cross folder and just run the make command on there. Basically, MPY cross is a tool that compiles Python code into a byte code that MicroPython can interpret. And so a lot of the ports, as an optimization step, will pre-compile certain Python code into byte code so that it takes up less memory. And so this needs that tool to be created to do that. So we'll run this step, and this actually ends up compiling a lot of the MicroPython source code itself also. And so that's why you see all of these CC commands, or it's just compiling different source files from MicroPython. Okay, so that succeeds, so everything's all good. And this all works. You don't need to worry about installing the GCC compiler. By default, right now, this Vagrant VM is using the GCC ARM embedded 6.2 release. So that's pretty cutting edge version of GCC. It's almost I think the most recent. I think they're almost up to 7, I want to say, for ARM support. So this is a pretty up there version, which is cool. But we'll see in a second that it actually causes a little bit of trouble because these later versions of GCC are better at catching errors. And unfortunately, you can see with a big code base like this, sometimes when you use an older version of GCC, you can get away with things that newer versions will complain a little bit about. But anyways, okay, so at this point, now that MPY cross is built, it mentions inside of the NRF folder, that's where you want to go, and you can use the make command to build the firmware. But you want to pick which board that you want to build the firmware for. And it actually mentions these are the targets that are supported right now. So you can actually build for the microbit, for the nRF51, but the Feather 52 is what we want to do for our nRF52 Feather right here. It mentions a few other boards here. I believe these PCA boards are the dev boards from Nordic. I believe you can get some of these dev boards. You might need to do a little more research and see what exactly these dev boards are. So just be aware. But the Feather nRF52 is what we're going to use. This table is really handy because it also mentioned another thing. So the Bluetooth stack, or the SD, you'll see it mentioned as. It's called the soft device. This is kind of the way that Bluetooth works on all of these Nordic devices. There's this binary blob that you have to install that is the code for the Bluetooth stack. So it knows how to talk to the radio hardware built into the chip and implement the entire Bluetooth Low Energy protocol, which is a non-trivial protocol. Like there's 7 different layers to it, all the way from the low-level radio communication up to the higher-level concepts at like the network level. It's a very kind of full-featured wireless protocol. So it's a little tricky, and I don't even know if there are good open source implementations of it yet. I believe the Apache Zephyr, or maybe it's the Linux Foundation, the Zephyr project, I think, has an implementation of the Bluetooth Low Energy stack, but it's a little bit new. It's only a few years old, and so it's evolving a little bit, and each implementation seems to have different levels of support and bugs and issues. But with these Nordic chips, you're kind of stuck with, at least right now, as far as I know, using Nordic soft device. And again, it's a bit of a black box. It's a compiled bit of code that Nordic gives you and just says, run it on the chip, trust us, it's going to work. And then if you call these certain functions, we'll give you access to the Bluetooth Low Energy stuff. So there are different versions of this soft device. And so this is kind of nice in the table. They tell you for the Feather board, there's this S132 version of the soft device that you need to use. It also tells you how to flash the chip because, again, for all these Nordic nRF52 devices, they kind of need their own serial to USB interface. And so that might control or impact how you actually get your firmware onto the chip. Like on the Feather 52, the way we have it built and supported, you can use this DFU, this device firmware update protocol, to update the firmware on the chip just using the USB port. But for some of these other boards, they mentioned Segur, and that means you need to use a tool like a Segur J-Link, which is like a nice little JTAG or single wire debug protocol tool that you can use to basically, you connect to your computer, and then your computer can just connect to an ARM Cortex chip, and using either a JTAG or an SWD protocol, just program that chip directly, regardless of whatever horrible state the chip has gotten into. It could be running the most broken code in the world. But the nice thing with those SWD and JTAG protocols is they get in at a very low level and they can just rewrite the chip's memory and put new firmware onto it. The tricky thing is you need this expensive J-Link device. The retail version, I think, is like $300. There's an educational one for about 100 or so. Really handy tool if you're developing for lots of different ARM microcontrollers because it works really well and it's super well supported. But if you just want to get some code running on a board, it's a little bit annoying. Luckily, you don't have to worry about that with the nRF52, and we'll use this DFU mode. But we'll see there's a little bit of setup we have to do to make that work. Okay, so it does mention here, by default, it's going to compile firmware for this PCA 140 board, which we don't want to use. We want to use the Feather 52 board. And so it mentions if you want to build for a different board, you run the make command and you tell it the board that you want. And so that's where we need to specify the target down here, the Feather 52 target. So let's do that. Let's go into the NRF folder and let's run make board equals Feather 52. And let's see what happens. So this is going to go through and it's going to start compiling all the MicroPython source code, and it's compiling it for the Feather 52 board configuration here. But we'll see in a second that it's going to run into a problem. And so we'll give it a moment here to compile the code. And I'll show you, there's basically, the problem is the version of GCC that we're using to compile this code is a little bit newer, and it's better at error checking, and it finds, unfortunately, a couple errors in the code base that older versions of GCC didn't find. So this is the first error that you're going to run into. So it's saying in the FATFS port, so this is a port of the FAT file system, which is kind of how MicroPython stores your Python code in flash memory. There's a problem here where it's saying that there's some line of code that's taking the value 2036 and shifting it left 25 positions. And so it's realizing that, oh, if you're shifting that 25 positions to the left, you're going to need 37 bits to represent that true value. But if this is a 32-bit value, what happens to those 5 bits that get shifted off the end there? And so this is a warning typically, and then the way that this source tree is set up, any warning turns into an error, which is smart because that kind of lets you know that, hey, just FYI, you might be doing something you don't expect here. Like, you know, if I really expected this 2036 value to be shifted 25 times over and, you know, represent some larger value, then I need to either like increase the size of this constant from like maybe a 64-bit integer, like a long potentially, or what I'm going to do is I'm actually going to turn off this error. So this is, you know, maybe this is a good thing, maybe this is a bad thing. You know, ultimately, someone needs to dig into the code and figure out what's the real intent here. You know, maybe it doesn't care about this overflow that's going to happen, or maybe this is some critical component of the FAT file system. From what I saw, ignoring the error seems okay, and we can move on, and it loads and the firmware seems to work. So, you know, just word the wise, there is an error that we're going to ignore, but I'll show you how to ignore an error like this. So what we want to do is we want to copy this part right here. So this is the name of the error that GCC is telling me. It's this shift overflow error. And so it's telling me that, hey, because this command line parameter was specified, GCC is treating this warning as an error and just halting compilation completely. But if I edit, so run nano on makefile. So this is the main file that controls the compilation of this port. If we go down a little ways, we'll see where all of the GCC options are set. And so there are all these includes right here. This includes plus. This just tells what folders to include when GCC is compiling things. But the C flags down here, so these little lines right here control all the command line parameters that are sent into the compiler. And here's where we can tell the compiler, like, hey, for example, this W all option right here, /WALL, that's saying turn on every warning, and then this W error is telling the compiler make every warning an error, so stop the compilation. Because normally, like, that shift overflow would just be a warning, and it would just scroll by as it compiles. It would just say, hey, oh, you're doing something weird here. Well, we're going on and finishing the compile because maybe it's not weird. But this W error option says, hey, stop, just let me see that error and see what's going on. Now I could turn that off, I could remove W error, but I'm going to keep that on because it's smart to keep that on, especially with a code base that's a little bit new and like evolving, and especially if I'm using a newer compiler against it, it's good to find those errors and things. But what I can do is I can add an extra option in here. So if I do -W, NO, so no, and then dash, and then if I paste in that shift dash overflow, I just pasted in the wrong line right here. I want to paste in the name of the error that I care about. So it's shift dash overflow is what it's called. And so that -W no shift overflow, that option is going to tell the compiler, hey, if you get that shift overflow error or warning, just ignore it. Just move on. Let it compile. Don't stop anything. So it's kind of like the big red hammer out of the giant option to just say, you know what, I'm not going to fix this right now. Just go on and finish. So let's save this file and let's rerun that make command again, and we'll see what happens. It's going to try to, you see, it didn't error again with that same error at least, but we'll see it's going to run into another error. So right here, it's telling me that a value is defined but not used. So this unused const variable error right here. So I'm actually going to copy that out so I can paste it in. And again, this is another case where this one's actually pretty harmless, because it's just telling me that, hey, you defined some variable and you never used it. That's normally a warning, and then because we've told it to make warnings into errors, it's actually failing the compilation right here. I could probably go in and just comment out that line under the assumption that nothing in the code is using it. But what I'm going to do is just tell it to ignore this error. This one I feel pretty confident about, although this is maybe a warning sign of like, hey, why are you defining a variable if you're not using it? Maybe you meant to use that. Do you have like a spelling mistake potentially somewhere? I think in this case the code base is okay, and especially as a code base is kind of brand new, you sometimes might have some code that you want to refactor out later. But let's do the same thing. Let's edit the make file. We'll go down to the C flags down here, and we'll just add an extra no. I think it was like the const something or other message. So dash uppercase W no dash, and then let's paste in the unused const variable is the name of it, like that. So you want that line to look like that. And as of at least right now on this day, if I run the make command again, it seems to compile the firmware. If you run into more errors, you might need to kind of take them as they come. Look and see, does this look like something that's innocuous and not a big deal and I can just ignore it, or maybe I need to go into the source code to figure out what's going on. You never really know until you compile some of this stuff. And again, we're only running into this because we're using the latest version of GCC, that 6.2 version that seems to be better about catching these errors. If you're using an older version, like I would bet 5.4 or something like that, probably doesn't run into these errors, which doesn't necessarily mean it's a good reason to use 5.4 just because it's not finding these errors. It's probably a good reason to use the newer compiler and just realize where these mistakes are and how you want to handle them, either ignore them or maybe try and change the code to support it. Okay, so we built the firmware. So the next step here is basically, if we compile the firmware just as we did, it's actually not including the Bluetooth low energy support. And so like I mentioned, there's that magic binary blob, the soft device that you have to get from Nordic in order to have Bluetooth low energy support. And the cool thing is, in this repository, there's actually a little shell script that you can run that will just go and download that binary blob for you. It grabs the Nordic SDK and I think it pulls the file out of there. So let's just run this little command right here, this Bluetooth stack download command. So it's going to download the different versions of the soft device, and then it's okay. So it finishes. So we've got the different versions there, and now I want to actually rerun the make command, but it mentions right here. So if you want to add Bluetooth support, you first run this download command, and you just have to run this once. I think this just downloads all the latest versions, and then what you want to do is you want to run the make command with this SD option at the top here. So you need to pick an SD and tell it the version of the soft device that you want. And so for the Feather52, like it mentions in the table, we want the S132 version of the soft device. So let's rerun the make command, and let's add that SD equals SD132 to the command. And let's see. It's mad about something. So let's run the clean command, because basically clean is just going to delete any of the files it created, and it will let me rerun make entirely. So let's rerun the make command, and now this time let's run with the board and the SD, and this will hopefully, oh boy, what is this thing mad about? Let's see. This was working right before I tried this stream, so I wonder if something is wrong. Let's see, S132. Oh, I'm adding SD132. Sorry, it's make SD equals S132, not SD132. So, okay, so that's what we want to do. So we're going to run this make. It's going to rebuild the firmware for this. And so we'll give this a moment to finish. And then after this, it mentions you want to run the make SD command. And so what this is, let's see. Oh, actually, no, we don't want to run this one yet. So this will trigger a flash of the Bluetooth stack. So yeah, we don't want to do this one yet. So for the Feather board, what the make SD would try to do is actually like flash that soft device onto your chip. We'll try that in a second maybe, but first let's go and get the DFU process set up. Like I mentioned, DFU is how you get firmware onto the Feather nRF52 board. And so there's a little bit of setup that you need to do. It's this Dfu Targets section where you basically need to install the Arduino package that we have, and there's this little nRF52 Python tool that we have inside of there that basically takes the firmware and uses that DFU protocol to send it to the chip. So it's kind of funny, this GitHub repository ends up using Adafruit's GitHub repository to make this work. But hey, it's an open source tool. You can definitely do that. Okay, so we built our firmware again. It just compiled, but this time you can see it included this S132. Basically, it's including the soft device 132 version inside of it. So we're including that soft device. Okay, so let's go now and let's do the setup for this Dfu targets. Now, the way the Dfu works, basically, you're going to have this firmware and you're going to push it to your chip. With the SAMD21, you use the BossSC tool to do that. With an Arduino, you use like the AVR man or AVR dude tool to push your firmware onto the chip. With the nRF tool, we're going to use, or with the nRF52, we're going to use this nRF tool, nRF command to push the firmware onto the chip. So every chip is a little bit different about how they do it. This is how we're going to do it for this chip. So it mentions there's some setup you need to do to make this work. Now the tricky thing is you need from either your computer that this chip is physically connected to. You could install these nRF52 utilities. You could install this nRF util package and flash from your computer, not from the virtual machine. That's one option. It just means that you're going to have Python installed. You're going to need pip. You're going to need a few Python packages and things running. And on Windows, it gets a little tricky to install all that stuff. So what I would suggest, and what I'll show here, is we'll actually set up our little virtual machine that we're using to compile the firmware. We're going to set that up to be able to use the Dfu util. And so our virtual machine is what's actually going to flash our chip. Now this is going to require one magic step where we're going to need to tell our virtual machine that there's a device connected to our physical computer that I want to pass through into the virtual machine so that the virtual machine can talk to a device that's connected to my computer. Because as far as this virtual machine is concerned, it's a real computer inside of another computer, but there's nothing connected to it. You know, there's basically this SSH terminal that I'm able to connect into and run commands in it. But if I connect this chip to my computer, it's connected to my physical computer, but it's not connected to the virtual machine inside of it. So I'll show you there's a step that we can do in our virtual machine's configuration to say, hey, this device that's physically connected to my computer, actually connect it to the virtual machine inside of my computer. And then at that point, I can use all these Dfu utils and things to program the chip. So let's go through and we'll do this setup, this Dfu target setup on my virtual machine. So again, still within this virtual machine, we're going to run some of these commands. The first thing I need to do, so it mentions you need to run this apt-get install command. Most of these are already installed. So actually the only thing I need to install is the Python pip package. That's one thing that's not installed right now in our virtual machine. So I'll do sudo apt-get install python-pip. And so this is going to install the pip package manager. And so we'll give this a second here to download the latest version. Well, it's not actually getting the latest version. It's getting the latest version from Ubuntu, which is probably quite old compared to what Python uses. But it's fine. It's still going to work. I'm going to go back to the home directory. It's the Vagrant user that you're logged in as right now, because I don't want to install this tool inside the MicroPython GitHub repository. I'm actually going to clone it into another top-level directory. So I went back to my home directory where you can see, this has that MicroPython folder. This is where the nRF52 fork has its source code that we just compiled. But anyways, I'm going to run this git clone, and this is actually cloning the Arduino package for our nRF52 feather. So we're going to run this command, and we're going to clone it into our virtual machine. And we're not going to use Arduino. This is only getting the source code for this so that it can install this nRF util package inside of there. And so it mentions that we're going to change into this tools directory inside of here. So let's do that. And so we're inside this nRF util tools directory. And then I need to run the sudo pip install -r requirements.txt. So this is going to just do a one-time setup to install all the dependencies of this Python tool. So it's going to do that. And make sure that you see at the very end, like successfully installed. If you see an error like, failed to finish, then don't move on. It meant that pip ran into some problem. And maybe like you might not have, for example, if you're not using this virtual machine, and if you're doing this on your own, like your Mac or your Linux machine, you might need to go and make sure you have things like Python installed, obviously, maybe these libffi packages, stuff like this. You might need to kind of decode based on these dependencies what you need to install for this. But if it doesn't work, again, go back to this virtual machine, and the steps that I'm running through right here should work on any machine. any machine that's running this virtual machine, basically. Okay, so I ran that pip install requirements, and then I need to run python setup.py install. This is going to install the nRF52 tool, so we'll do that. And this is just a one-time install process. So now this nRF52 tool is installed, so I just need to do this once on this virtual machine. And if I run nRF52, this actually shows me this is the command it's going to use to do that Dfu firmware update. So I do that once to get the tool installed, and now it mentions I can actually flash this board using a few different commands. So you make your firmware like this, so it's mentioning you specify the board and the soft device that you want. Then you run this dfu gen command that tells it to generate the firmware that's in a format that can use that dfu utility. And then you run this dfu flash command that's actually going to use the dfu utility to flash the firmware that was just built to the chip that it finds connected to your computer. So we're going to do that. But before I can do that, like I mentioned, here's kind of the problem. So I'm going to plug in this chip, this device to my computer, and we'll see kind of what happens here. So if in my virtual machine, I'm going to list all of the USB serial devices. So if I do ls-l dev tty star, this is listing all of the serial devices that this virtual machine knows about. And you get all these standard ones that Linux creates. So there's like the TTY 0 through 50 something devices here. But I don't see anything that's TTY USB. That's usually what you see in Linux, like /dev/TTY USB 0. That means if I had like a USB to UART device connected, that's usually what it's going to be called. So that kind of tells me my virtual machine does not see this chip connected to my computer. Now I'm going to open a new tab. This is a tab on my Mac, not on the virtual machine. And we can actually see if I list the tty.star devices on my Mac, here is this slab USB to UART. This is the Scilab's USB to UART. So that's actually the USB to UART chip that's on this NRF feather. So my Mac can see the nRF52 feather, but my virtual machine cannot see it. We'll fix that. So what I want to do with VirtualBox, if I run VirtualBox, this is the engine that's actually powering the virtual machine that we're running in the background. You can actually see right here, this is this atmel samd MicroPython Vagrant. This is the virtual machine. It's kind of cool. It shows it's running. This is the virtual machine that's running right here with that little Linux console that's open. So it's running right now, but luckily you can actually edit some of the settings inside of here. So if you right click and go to settings, this lets you change some of the settings for this virtual machine. If I go to ports and then over to the USB, this is kind of cool. So this is where I can actually tell VirtualBox that if there is a device connected to my physical computer, actually grab it and pass it through to my virtual machine, my virtual computer inside of there. And it actually means that my physical computer cannot see that device anymore. It removes it from my physical computer. My Mac will not be able to see that device, and only my Linux virtual machine will be able to see it. Now, there are a few devices that are added by default. That's because this Vagrant configuration file automatically sets itself up to add this, basically our Adafruit devices, our SAMD21 boards are added automatically to this. But we can add this Scilab's USB to UART device as a little manual pass-through, or they call it a USB filter, because basically whenever VirtualBox sees a device connected to your computer, if that device is mentioned in a filter, then it will grab that device and actually pass it through. So what you want to do is click this little add on the right side. This is going to list all of the devices that are connected to your computer right now. And look for the Silicon Labs, the CP2104 USB to UART bridge. That's what your Feather nRF52 is going to look like. So I'm going to click that. That's going to add a configuration here. I don't actually need to change anything, but if you want, you can edit this filter. So what it's going to do, it's going to look for a device with this vendor ID and this product ID and this revision number. And whenever it sees that thing connected, it might even do based on the serial port or serial number. Whenever it sees that connected, then it's going to connect it to your virtual machine. So this is fine. I'm just going to cancel out of here. We'll just leave the defaults. We'll say OK. It's going to save the settings. Now here's the thing. It only applies this logic when it sees a device connected or disconnected from your machine. So what I have to do is disconnect it and reconnect it to my computer. And so now it should be doing the pass-through. So I'm going to go back, and on my Mac, let's list the USB serial devices again. So this is good. I don't see it on my Mac, but now if I go back to my virtual machine, let's list my serial devices again. And hopefully, yeah, here we go. Let's check this out. Dev TTY USB 0. So we didn't see this before, but now I see it. And this is telling me that that Scilab's USB to UART device, and if you really want to see, run the ls USB command. This is going to list all the USB devices that are visible to your computer. And for this virtual machine, you really only see this CP210X UART bridge device. You know, there's not much else. There's like a hub that I think VirtualBox adds to your machine. So this is kind of funny. Oh, this is funny. The name MyAVR Smart USB Lite. Interesting. I guess there's some kernel driver that assumes that any Scilab CP210X device is a MyAVR Smart USB Lite. Interesting. I haven't seen that. But it doesn't matter. Who cares what this thing's called? As long as you see this Dev TTY USB 0 device, that's the magic thing that you need to see right here in order to make this DFU from the virtual machine work. Okay, so at this point now, let's run this command. I've already run this make command, and so I need to go back into that nRF folder in the MicroPython source directory. So if I go back into the MicroPython and then the nRF folder, I've already run this make command right here that compiles the firmware. So let's do the dfu gen command next. So let's run that. And so this just builds this DFU package. And then here's the magic step. We're going to run this Dfu Flash command with our board plugged in and with the device passed through to our virtual machine. Now you'll see something that's going to happen here. Let's see. We'll run this. It fails, unfortunately. It's telling me that undefined make flag serial example serial equals dev tty USB 0. I guess for whatever reason, maybe the documentation of this port isn't up to date, but there's an extra environment variable that needs to be set right here. So luckily it fails, and it gives me a hint as to what I need to do. So I need to define this serial parameter and point it at what's the serial device that we're actually going to do this Dfu Flash against. So let's rerun this command, but before Dfu Flash, let's add serial equals dev tty USB 0. So I'm going to pass in the path to that USB to UART device /dev/tty USB 0, just like this, and then run the Dfu Flash command from the make file. So let's run this, and this is good. Notice the light is flashing on the board. That's telling me that the DFU is happening. We're noticing here it's doing its magic. It's sending everything to the board, and we'll give it a moment here. It just takes it maybe a minute to flash the firmware, and then we'll have MicroPython hopefully running on the Feather nRF52. At the very end here, it kind of stops for a second. I think it might be doing some kind of verification. And then in a second, it should hopefully finish. Okay, device program, so that's good. So now our board hopefully is running MicroPython. Now the cool thing is this still shows up if I list the USB to serial devices. You know, I still see this dev tty USB 0. For some reason, the screen command, so normally you would be able to use like the screen command to connect to that USB to serial device and see the Python REPL. But I think in the VirtualBox environment, for some reason, the screen command just doesn't work. So you can try it, USB dev tty USB 0 115200 baud, but screen just instantly terminates. So unfortunately at this point, what I noticed I have to do is I have to turn off that USB pass-through, because what I'm going to do is I'm going to access the REPL from my Mac. So I'm not going to use the virtual machine anymore. Basically, the virtual machine I'm only using to compile and flash the firmware. And then when I want to actually connect and start using MicroPython, I'm going to do it from a serial terminal on my machine. So if you're on Windows, you could use PuTTY. If you're on Linux, you could use the screen command. On Mac, you could use the screen command. So whatever serial tool you like to use, you can use it in this case. But in order to make this work on my machine, I need to turn off that USB pass-through, because like I mentioned, it's an all or nothing thing. When my virtual machine has the USB device, then my physical Mac cannot use it. They both can't share the same device. Either my VM has it or my physical machine has it, not both of them, unfortunately. So I'm going to go back to VirtualBox, and I'm going to go back to the settings and go to the ports again and the USB config. I'm just going to uncheck that Scilab's device right here. It's kind of nice. It'll still remember it, but if I uncheck it, it will disable that filter. I'll say OK. And then the annoying thing is you're going to have to unplug it and replug it to get it connected to your Mac or your machine again. So I just did that. And if I list the USB devices, yeah, now I don't see that USB 0 device anymore on my virtual machine. At this point, I'm done with the virtual machine. I'm going to go back to my Mac right here, and now I see there's my Scilab USB to UART device. So cool. Okay, so let's connect to it. So I'm going to run the screen command, dev tty Scilab's USB to UART 115200 baud, and I don't see anything, but I press enter, and hey, check that out. I've got a Python prompt. I'll say hello world. Look at that, we've got Python code. If I press Control D, D as in dog, that's going to tell it to do a reset. So I do that, and I see MicroPython. Oh, so here's the version. It's not 1.9. It's version 1.8.1, and it's the Bluefruit nRF52 feather. So that's pretty cool. Looks like it's running. So I've just successfully flashed the MicroPython firmware onto this device. Okay, so you're probably wondering, well, what can I do now? I've got it running on here. I can do some basic stuff with this. And it mentions at the top, actually, what are the supported features. So again, this is using the MicroPython API. So you're going to want to go to micropython.org, look at the documentation there, and see, this is using the machine API, presumably, to access all the hardware. So this is not using CircuitPython. Eventually, we'll probably have a port of CircuitPython to that nRF52. But again, so you'll want to look at MicroPython docs to see how this stuff works. And again, all of this is like still super early. Don't expect any of this stuff to be rock solid or to completely work. It does mention there is Bluetooth Low Energy support though, so there is some basic support inside of here. You can even do a REPL over Bluetooth Low Energy. I haven't tried this yet, so this is maybe a future stream I might play with this, but there are a few examples. So in that NRF directory in the fork of MicroPython that implements this nRF52, there is an examples folder, and so this is kind of handy. This actually shows a few examples of what you can do, because as far as I know, there's no specific documentation for this port yet. But let's look at this uBluePy scan. So this is like a micro BluePy, like a Bluetooth Low Energy API that's been added to this port. And so this kind of shows you how to do some basic things. This is going to scan for Bluetooth Low Energy devices that it looks for. And so it kind of shows some basic usage here. There's a scanner class, it looks like, inside this uBluePy or MicroBluePy API. And it looks like in the scanner, you have to run this scan function. I believe you tell it how many milliseconds to scan for, and then it's going to return whatever devices it found and all this Bluetooth metadata about those devices. Let's use this. Now, I ran into a little bit of trouble, though. So normally in MicroPython, if you press Control E is in like Eric, that will put you into this paste mode where you can copy source code and paste it in, and it won't mess up all the indentation. Because sometimes if you try to paste source code into the REPL, you'll see that it just keeps adding all this indentation. But if you press Control E, you get into this paste mode. So what I can do is I can select all of this source code, and if I can copy this, and then if I just paste this in, you can see it pastes in code. Now, we'll see in a second. It says press Control D to finish. So I'm going to press Control D, D as in dog. Normally that resets, but when you're in this paste mode, it doesn't reset. And it tries to run all the code that you just pasted in. And it gives me a syntax error. But if you go back and look at this, it didn't actually paste in the code correctly. Like def BYOSTR, that's not actually the code here. It's bytes to str. So it missed, this TE, or it turned that into an O, or you just completely mangled this. And if you look through, it really mangles a lot of this, like this FEBY name. No, that's actually find device by name that it should have gotten. So I think this is probably a bug in this port, probably with the buffering between the nRF52 and the USB to UART bridge. I'm guessing that, there's maybe not enough buffering on the MicroPython side, so that, the USB to UART chip, which is actually what's receiving, when I click paste, all of that command is getting sent from my Mac to that little Scilabs chip on here over a USB serial connection. And then the Scilabs chip is converting that into a serial connection that's connected to the nRF52 module right here. But if that nRF52 module isn't reading all the data as fast as the Scilabs chip is sending it, it might lose data. And that's a real common issue sometimes, if you don't have buffering enabled, or if you're not reading fast enough, or if your buffer isn't big enough, you might lose data like this. So I think there's probably a bug in this port right now with how it defines the buffering for the serial port or the REPL connection. And it looks like it loses data when you send a lot of data to it. So it makes it a little tricky, because I noticed even trying to use like the AMPI tool to copy a file to this board, you run into this problem. So just be aware, like this is useful for testing right now, but maybe not for building a rock solid kind of device just yet. But we can still run enough of this code to kind of just see that some of this Bluetooth stuff works. So let's copy this import. This is going to use the MicroBluePy library to import that scanner object. So let's run that. So we'll run that import. That succeeds, so that's good. I mean, that means that that library was loaded and that it was compiled in, and at least enough of that is hopefully going to work. And then the way this code works, it looks like you create an instance of the scanner class from that MicroBluePy module, and you call this scan function, and it's going to return back the devices that it found during the scan. So let's make that scanner. So we'll say s equals scanner, since we've directly imported it. And let's just say results equals s.scan, and then you need to pass in a number. And again, there's no documentation on this. You're probably gonna have to look at the source code to figure out kind of what this means, but I think this is the amount of time to scan for devices. Now, I have this little fitness tracker right here. This thing uses Bluetooth Low Energy, so in theory, it should be able to see this, this tracker right next to this, you know, even in the same room right here. But I'm gonna tell it to scan for 2,000 milliseconds. I think this will scan for like 2 seconds. So we'll let it do that. So hopefully it's gonna listen. Yeah, it looks like it returned after 2 seconds. And let's see what's inside of results. So, okay, so there's a scan entry inside of there. And then let's see how we interpret this thing. So in the code, they call this get device names function, which they implement right here. And this basically goes through each of the scan entries and calls this get scan data function. So, okay, so in our results, it looks like there's one scan entry. So if I say my, say SCE equals results 0 dot get, let's see, what do they call this? It's get scan data. So get scan data. Okay, so now if I look at this SCE object, okay, so this is actually showing me something here. So this is basically a bunch of the Bluetooth Low Energy metadata that was advertised by hopefully this device. I actually haven't gone through to check it. But you can see, so Bluetooth Low Energy, like I mentioned, is somewhat of a complex protocol. I've done a bunch of videos on it where I kind of try to explain a little bit of it. If you look at the Feather nRF52 guide, it actually goes into a lot of good detail and kind of mentions a lot of Arduino examples that talk to you about Bluetooth Low Energy. I think this even links to some guides we've done on Bluetooth Low Energy itself. So, you know, it's not, you know, it's certainly more complex than just like sending and receiving data over a wireless connection. They're basically, each device has a number of services, and each service can have a number of characteristics, and each characteristic can have all these different traits and things associated with it. But basically you expose your data using these services and these characteristics, and then a device can advertise itself as a Bluetooth Low Energy device, and everything comes down to all these unique identifiers, these UUIDs. And so this is basically telling me that it found a device that's advertising itself using this short UUID value, and then there's like this service data that it encoded inside of there. So I'm not going to go into all the details of this because basically at this point, you know, you kind of need to know about these low levels of the Bluetooth Low Energy protocol right now because this is just a very low level API to access Bluetooth Low Energy, which makes sense. This is a brand new port. I'm sure in the future there will probably be a more standardized higher level API for this. But you're going to need to go through and parse out like this advertisement data and figure out, okay, is the device that I'm looking for available? If you look at the example code again, this scan device, it actually goes through and looks for basically devices that have advertised their name. So it looks like my little fitness tracker doesn't seem to advertise its name. But if you had a device, like a smart light bulb or something, it might be advertising its name. And then it can parse out those values, and then it just prints them out. And so this is a way where you could find some device that seems to be advertising itself with a certain name. But then once you find a device, then you actually need to connect to it and actually start communicating with the services and the characteristics that are on it. And there are some examples here. So this MicroBluePy Eddystone, I believe this one will connect to a device. Or no, maybe this, oh sorry, yeah, this example will make your nRF52 look like an Eddystone device, which is basically, if I remember correctly, Eddystone is it's like a proximity detection thing, or it's a way to advertise like, hey, here's like if you open up this Google app, I think it will scan for any of these Eddystone devices nearby and show you like, oh hey, you're in the Apple store and, by the way, like there's a sale on Apple devices. I think that was the dream of these things, but in reality, who knows if that's actually useful. But that's actually a cool demonstration, though, of what this Bluetooth Low Energy API can do, because so I was just showing, I was scanning for devices and it found my little fitness tracker. I could connect to that potentially and start reading data from it. But with this nRF52 device, it can actually act like a Bluetooth Low Energy peripheral. So my nRF52 could act like my fitness scanner or my fitness tracker right here and advertise itself as a Bluetooth Low Energy device. And so that's maybe another cool scenario where you could make a little MicroPython powered maybe sensor that's advertising itself over Bluetooth Low Energy to say, hey, I'm a temperature sensor. Anything that wants to connect to a temperature sensor, connect to me, and you can read my temperature data, for example. And so you could have like your iPhone or iPad or Android device, any little mobile device that has Bluetooth Low Energy. Even the web, there's a Bluetooth Low Energy web protocol where from JavaScript in a web browser on compatible devices and in a compatible browser, I think the Chrome browser supports it right now, you can actually scan for and find Bluetooth Low Energy devices and connect to them. So you could have your little temperature sensors, a whole network of them all around your house and using Bluetooth Low Energy, and you open up your tablet and you start to see like, oh, there's my, my living room temperature sensor. Let's connect to that and let's, see maybe a graph of all the temperature data. So you can imagine that's the kind of stuff you can do because the nRF52 can act as either a peripheral where it is in a Bluetooth Low Energy device that's advertising itself and things can connect to it and read and write data to it, or it can act as what's called a central device where the nRF52 will connect to other devices like your smart fitness band or your smart light bulbs or whatever is around your location tracking object for it. So that's one of the cool things that the 52 can do. The older nRF51, I don't believe it had that central mode where it can actually connect to other devices. It only had the peripheral mode where it could look like a device, but it couldn't actually connect to other devices. So the end thing though is that you're going to want to check out these examples because this is kind of the documentation right now to see how this Bluetooth Low Energy API works. And again, like I said, this is an early port, so I don't think everything is kind of supported. Kind of mentions here, so you can do peripheral on the nRF51. You can act like a device, and you can do central and peripheral on the nRF52. And so that's what I was mentioning. You can connect to devices as a central, or you can act like a device as a peripheral in that case. And there's some cool stuff here. So it does mention you can do a REPL over Bluetooth Low Energy. So maybe in a future stream I'll check that out. This has gone for about an hour, so I don't want to go too much longer in this stream. I just wanted to show this is kind of maybe the current state of the world for MicroPython on the nRF52 based development boards like the nRF52 Feather right here. So it's kind of cool. You can see, it's maybe not for the complete beginner because you're gonna have to compile this firmware. Again, it's brand new. I think it's only about a month old, or like that's the last time this repository was updated. So it's kind of cutting edge stuff right here, but worth kind of checking out and exploring because I think this will be really cool probably a year from now once there's a stable nRF52 firmware and maybe even up in the upstream MicroPython, or if we have like a CircuitPython version. It could be pretty cool to have a Python API to create Bluetooth Low Energy devices, because one big challenge I found with Bluetooth Low Energy is that the APIs to use it are a little difficult. There's no cross-platform API that I've really seen because there are a lot of challenges in that how OS X on your Mac exposes Bluetooth Low Energy is completely different than how Linux exposes it. And it's completely different than how Windows exposes it. And even like early versions like Windows 7 doesn't even support Bluetooth Low Energy at all. It's only Windows 8 and really not until Windows 10 that you had an API that you could use in your own programmatic code to access it. So just various levels of support make it really challenging to have a uniform API. So it's really hard to make a Bluetooth device that has your own services, your own thing, and an application that can talk to that device that's an application for like your desktop computer. It's a little better on the mobile world because like I said, iOS and Android at least have had Bluetooth Low Energy APIs that are finally, after about 5 years, stabilized and somewhat bug-free and somewhat usable. So your best shot for creating a Bluetooth Low Energy app is with a mobile device, like using iOS or Android, just because those are maybe the most stable and best platforms for accessing the APIs. But this could be kind of cool because, if I've got a device like the nRF52 that can act as a central where it can connect to Bluetooth Low Energy devices and it can act as a peripheral. It can advertise itself as a Bluetooth Low Energy device. Well, then I've just removed the need for my computer's Bluetooth Low Energy radio and all of its confusing and complex APIs completely. So I could build some kind of cool system where, maybe I've got one little nRF52 feather that's my central device that can connect to all of my other devices, and I've got all this MicroPython code that's using the Bluetooth Low Energy APIs and connecting to my sensors and reading them and controlling them, or maybe it's my smart light bulbs and telling them to turn on and off. And then if I want to add devices to this network, I add another feather nRF52, but I make it act as a central, or act as a peripheral. So now it's a device that my central device can connect to. So I've got all these peripheral devices that are like my sensors, my light bulbs, my relays, everything I want to control. And then I've got my central device that's able to control those. And it's all from the same MicroPython API, which is really cool. And that's something that's pretty challenging right now because, if you want to make something act like a device, sure, you're going to, you could write some Arduino-based code potentially, or maybe this MicroPython-based code. But then if you want your computer or your tablet to control it, well, you got to go figure out your iOS or your Android API to make that work. So I think this will be cool. I think we'll see a lot more in the future, and maybe this will make Bluetooth Low Energy a little bit easier to use because, at this point, you've got a consistent environment. You're basically just saying, hey, just forget that radio on your computer and use the one connected to it right here just because it's easier to program it in some ways. So that's something cool to look forward to. I'm going to wrap up the stream then. So if folks have questions, throw them into the chat. And I'll jump back to that. Let's see, let me go to the main headshot here. So yeah, there we are. Let's see. Someone's wondering, wouldn't it be safer to disable the warnings for those specific files instead of globally? Oh, that's a good point. So someone is suggesting, as we saw, when I compiled the firmware for this, I have to disable some of the errors because I'm using a later version of GCC. Yeah, you're right. I think you can go into source files and you can add a line at the top. There's like a pragma. If you Google search, I'm sure you'll find what it is. But so you can turn off at a file level some of the warnings, or you can take the big hammer that just turns them off globally. You're probably right. The safer option is probably to disable them at a file level. But I figured let's just get something compiled and running. Ultimately, the fix would be to go in and change the source code. For that unused constant error, we'd probably just need to remove that constant if it's not used, or just figure out maybe it really should be used. And for the other error, that's that shifting error, it probably just means that I'm guessing either the type needs to be expanded to like a 64-bit type, or maybe the code really does want to shift it out of range, and it wants it to overflow and get that behavior. It's sometimes a little convoluted, but since that's coming from the FAT file system code, that's actually source code that was pulled into MicroPython from another open source project, I think Elmchan's FATFS implementation. So I'm guessing that we don't want to change that code and just, it's doing that overflow for a reason. And it's just, this later version of GCC catches it. So in that case, maybe that is a case where you want to put into that file, hey, ignore this error on this specific file, or maybe just increase the size of that type and see, hope that you have enough tests to make sure that you can catch that. Let's see, someone's wondering, is it a chip that has Wi-Fi and web server? No, so yeah, this is the Feather nRF52. Like I mentioned, it's using the Nordic nRF52. So this is a Bluetooth Low Energy based wireless chip. So there's no Wi-Fi on this chip. There is a cool chip though that I've actually shown. I think I did a video on how to use the firmware for it. The ESP32, that's the latest version of the ESP8266. That's a chip that has both Bluetooth Low Energy, I think Bluetooth Classic also, and Wi-Fi on it. So that's a cool chip. Totally different chip though, from a different manufacturer, but might be worth checking out. And that one's actually made a lot of progress, I think, in the recent months. So you might check that out. And there is a MicroPython port of that that's closer to getting into upstream MicroPython. It's at least there's a MicroPython repository in the main MicroPython GitHub kind of organization, and I think there's a plan eventually to pull that into the upstream MicroPython repository. But long story short, yeah, this chip does not do Wi-Fi. It only does Bluetooth Low Energy, but it does Bluetooth Low Energy very well. Like I said, the Nordic devices are used quite a bit, and they're pretty stable. Nordic gives you that Bluetooth Low Energy soft device stack, which is a good and bad thing. It's it's kind of bad that well, it sucks you don't have access to the source code, so you don't really know what's going on inside of there. But it does seem to work. They do update it quite a bit, and it's used in a lot of devices and products and things like the Microbit, for example, uses it. So it's pretty well proven and known to work well. So it is a good option. So someone's wondering, would it be possible to fake other devices in close proximity and jam the communication? Yeah, so great question. So, can I make this little nRF52 dev board look like another Bluetooth Low Energy device? And yeah, you absolutely can. So if you have like this, this little fitness tracker that advertises as a Bluetooth Low Energy device, you can use a tool to scan for this device and see like what are all of the Bluetooth Low Energy services, what are the characteristics that it exposes. You can find all of those UUIDs for those things. You can reverse engineer all of this. In a lot of cases, in some cases, they're actually there's secure protocols over Bluetooth Low Energy now, where it's a little bit harder sometimes to connect to devices that use security. But if the device doesn't use a lot of security, you can see everything that this device exposes, and then you can program your nRF52 to act as a peripheral that advertises all of those exact same services and characteristics. So if I knew the services and characteristics that my fitness band exposed, I could program this device to advertise those. Something could connect to it, and as long as I implement, whatever protocol that, like if it's a step counter or a heart rate monitor, I probably want to implement that protocol. I could totally fake it out and, have my malicious smart tracker that, maybe sits around and hopes people connect to it, and maybe it tells you that your heart rate is like going 500 beats a minute. Get to the hospital now. That's not normal. So that could be some fun that you can have with this. So definitely, for sure, that's a cool thing that's somewhat unexplored with Bluetooth Low Energy, and that it's a very open and generic protocol, which opens the door to a lot of fun kind of hacks and interesting things you can do with it, because devices expose their characteristics and their abilities in kind of generic ways. So it gives you a lot of cool things. Like the nice thing with Bluetooth Low Energy is that you can access devices. Like you don't have to go and sign a waiver to get access to the protocols and the specs and things. They're all published online. So you can actually access this data, which makes it kind of interesting for makers to use it like this. So, okay, I think that was it as far as the questions go. Oh yeah, so right, someone's mentioning a lot of the firmware vendors are scared of releasing their firmware. Yeah, I mean, there's probably a good reason why Nordic keeps that firmware closed source for now. I'm guessing, maybe they're worried that someone hacks it or figures out, how different exploits they can use against devices. Although security by obscurity has been proven time and time again that, eventually it's going to get hacked or people are going to figure out what's going on. So I don't know, it's up to them. But I'm hoping eventually there will probably be some open source Bluetooth Low Energy implementations like that SD, that magic binary blob, for this device. Who knows, in the future, maybe there'll be an open source version that eventually becomes, maybe the canonical or the best implementation that people end up using for this. Like I said, there are some projects like the Apache's, I can't remember if it's Apache or not, but the Zephyr real-time operating system apparently has an implementation of a Bluetooth Low Energy stack that I think works on these NRF devices. So that could be another cool thing to look at in the future for this. So cool, I will wrap up the stream then. So thanks a lot for watching. This was how to compile and install firmware for MicroPython on the nRF52 Feather. So this is the new Bluetooth Low Energy board from Adafruit. It's kind of real popular and a cool option to use with MicroPython. So there's a great fork of MicroPython, like I mentioned. It was created by this Daniel, let me get his name correct again, Chalamatza, it looks like is his name. So he did a great job on the port. At least, it seems to have compile and run. I can get the REPL and start accessing some of the stuff. So it's worth checking out. And like I showed in this video, we used a virtual machine to compile the firmware because you need a nice Linux or Unix-based environment to compile, and in a lot of cases that's annoying to set up, so just make a virtual machine that sets it up. And then I showed how for the Feather nRF52 you can use this Dfu process to update the firmware over the USB connection so that you don't have to use a JTAG or a SWD connection. It gets more complex, you need all this expensive hardware. So this is cool. If you're using the Feather nRF52, you install some tools and you can get this Dfu process to work with it also. And we did that again from the virtual machine because it's a little bit easier to set up some of these tools in that environment. So cool, thanks a lot for watching. Check out youtube.com/Adafruit. You'll see this stream and all kinds of other fun project videos there. Check out twitch.tv/Adafruit. You'll see me stream these things live. I like to do a stream every Friday. I was in the middle. I had started last week, actually, this project, which we're going to come back to. This is basically the Circuit Walker sneakers, but I found this Bluetooth, this nRF52 port, and I wanted to do a quick little stream just while I finished up some of the Circuit Walker sneaker stuff. So tune in next week, and we will continue on the Circuit Walker sneaker project. But until next time, this is Tony from Adafruit. So thanks a lot for watching. Click the like, the comment, the subscribe. Let us know this is useful stuff, and we'll keep making content like this. Oh, and I just remembered, I meant to say this at the start of the stream. Unfortunately, I forgot until now. In the last stream that I did, in the first part of the Circuit Walker sneakers, I made a pretty nasty error in the code in that stream. So I forgot to update the elapsed time. And a viewer actually caught it, messaged me, let me know about it, and I fixed it in the GitHub code. So if you watch the first stream, it's updated in the code. So if you've downloaded the code, it's probably updated already there. But if you see weird erratic behavior, update the code, because I was not updating the elapsed time. So it was working, but that was just because it just happened to work because of a few different bugs that were in the code. So grab the latest version. In the next video I do on the Circuit Walker sneakers, I'll go back and also show the error that I made there. But it's fixed in the code that's on GitHub. That's linked from the video. So you'll get the latest code. You just might see, if you're following in the video, that it works sort of, but there's a big mistake that I made, unfortunately, with the code. So maybe if you watch the video, see if you can figure out the mistake as I go with it. So cool. Until next time, I will see you. So this is Tony from Adafruit. Thanks a lot for watching. I'll see you next time. Bye.